All right, welcome back. We continue on looking at Spearman's rank correlation, and we're going to be looking at some examples of its use and calculation. So the first example, example 5.1, we'll be looking at Spearman's rank correlation coefficient to assess the relationship between two quantitative measurements. The table below contains two continuous measurements on a sample of 10 experimental units. We've got 10 experimental units or 10 subjects on which we have measured both the x variable and the y variable. So each column here corresponds to an experimental unit, and we want to evaluate the relationship between these two variables. So what we have to do first would be to rank the x values, rank the y values separately, and then calculate the Spearman correlation. And so let's see how to do this. And I'm going to do this in the context of a spreadsheet. We've done this many times throughout the course. I like doing this with a spreadsheet because it gives you a visual representation of how we're actually processing the data, how we're actually doing the calculations. So it gives you a visual idea of what the formula represents. And so here I have a spreadsheet, and you can see here that I have input the data into the spreadsheet. The B column corresponds to the x variable, the C column corresponds to the y variable, and then rows correspond to the different subjects or experimental units. You can see here I've got some things programmed in. Some of these values down here we have to ignore for now. For example, anything that says Spearman, we really need to ignore this until we get everything processed. But you can see here that it's correctly calculating the number of observations as being 10. And I've also included the Pearson correlation between x and y so that we can compare it to the Spearman once we have completed that. Now, the first thing we need to do is to rank the values taken on by the x value. And we're going to do that independent of the ranking of the y values. And so the next step that we will do is to sort the x values in ascending order. So I'm going to go back one slide here. You can see here that I've got the data listed in observation order. And what I'm going to do is I'm going to sort these three columns to keep everything together, but I'm sorting based on the values in the x column. All right, so that's an important point. I'm talking about sorting independently of the y values, but in order to keep the values together, I've got to make sure that I sort those three columns together. But I'm sorting based on the contents of the values in the B column. And so when I do that, notice that the x values are now sorted in increasing order, and the observation numbers have changed accordingly. And by sorting all three of these columns together, we've kept the y values with their corresponding x values. That's very, very important. Now we need to assign the ranks for the x's. And we need to be careful. We need to check for ties. And if there are ties, then we need to do what we've done in the past in this course, and that is assign the average ranks. As we look down the column for the x's, we see in this case that there are no ties. And so the ranks then can be assigned 1 through 10 as I've done here. Now let me also just give you a word of caution that in spreadsheets there is typically a rank function, but you've got to be careful. The rank function in many spreadsheets does not handle ties correctly, or at least it does not handle ties the way we would need them to be handled. So what I've done here, I'm not relying on the rank function. I'm just hand entering in the ranks. Now that's a bit cumbersome, I understand that, but for pedagogical purposes, for teaching purposes, for showing how these calculations are done, I'm using this spreadsheet, and some aspects of this are going to be a little bit cumbersome just because the way the spreadsheet are programmed, they don't provide the type of calculation of ranks like we would require. Okay, so I've got the ranks, I've got the x values ranked. I've calculated the ranks for each of the x's. Then what we need to do, the next step, we're going to sort, and now we're going to sort the first 4 columns, and we're going to sort based on the values in the y column. And so when we do that, you can see that we now have the y values in ascending order. And note that all of these other 3 columns were arranged accordingly to keep the x and y values together. And now we've got these sorted, we need to calculate the ranks of the y's. And again, we need to look and see, are there any ties? And in this case, there are no ties. And so we can again enter the ranks of the y's as 1 through 10, as we've done here. As I'm entering these quantities, notice that these columns out here are changing. So let me go back a slide. And let me go back another slide. In fact, one more. Okay, so you can see here that these two columns have zeros out here. These are programmed in to calculate the difference between these two columns, and then this column is the square of that value. And so once we start populating the columns for the ranks, these start changing. All right, so then we enter in the ranks for the y's, and now we have everything we need to calculate the difference in the ranks, the squared differences, and then to calculate the Spearman correlation. Now notice that I've got two cells for the Spearman correlation. The first cell right here, this is using the definition formula, and then the second cell below that, that is using the shortcut formula. Now, for this example, the Pearson correlation between x and y is 0.69859. So that would be considered a high, moderate to a strong correlation in most situations. The Spearman correlation is very close to that, 0.69697. Now, that's not always going to be the case. There are going to be some situations where the Pearson correlation and the Spearman correlation are somewhat different, and that's to be expected because they're based on different quantities and they have different characteristics. But in this case, they're fairly close. Now, note also that the value for the Spearman correlation that we obtain using the shortcut formula is the same as it is using the definition formula, and that is because there are no ties. So when there are no ties, the shortcut formula will give the same value, the correct value for the Spearman correlation. So that is the process that we can use to go through to calculate the Spearman correlation. All right, you can visually see that process we go through. All right, let's now see how to calculate the Spearman correlation and also to test the hypothesis that the population Spearman correlation for the population from which these data were obtained, whether or not that Spearman correlation is zero or not. And we're going to do this using SAS. And so I have a data step to create a SAS data set for these data. And then the code, the SAS code to perform the correlation analysis is very simple. Again, it's the same as it was that I showed in that template. Now notice that I have included the Pearson option here. Again, that's unnecessary because by default, SAS is going to do a Pearson correlation analysis. But I've shown it here just so that you can see that that is an option. If you wanted to include that for clarity's sake, you could. But anyway, I'm including the Spearman option. And so that is going to instruct SAS to perform a Spearman correlation analysis as well. And here is the output from that correlation analysis done in SAS. The first thing we have up here, well, the first thing we have, it's telling us the two variables that we're doing the correlation analysis for. Then it gives us a table of univariate summary statistics for the x variable. It gives us the number of observations, the mean of those x values, the standard deviation of the x values, the median, the minimum, and the maximum, and it gives those same summary statistics for the y variable. And then it gives us two correlation analyses. The first, you can see, this is what SAS produces by default. That's the Pearson correlation coefficient analysis. And you can see here in this two-way table that the Pearson correlation is calculated to be 0.69859. Now let me go back and show you that's what we got here, 0.69859. So that's the same exact value we got in the spreadsheet. Below that, we have the table for the Spearman correlation analysis. And the calculated value of the Spearman correlation is 0.69697. All right, now let's again go back to our spreadsheet, 0.69697. All right, so that's the same exact value we got with the spreadsheet. Now, in addition to calculating the Pearson correlation and the Spearman correlation, SAS ProcCore is also going to test the hypothesis that the corresponding correlation coefficients are zero against the alternative that they're non-zero. And the p-values for those tests are given below the point estimates. And so this value here that I'm circling, the 0.0246, that is the p-value for the test of the null hypothesis that the Pearson correlation coefficient at the population level is zero against the alternative hypothesis that the Pearson correlation coefficient at the population level is non-zero. And so you can see here that if you were testing this hypothesis at, let's say, 0.05 level of significance, you would conclude then that the Pearson correlation at the population level is non-zero. Similarly, the Spearman correlation analysis down below, SAS includes the p-value for testing the hypothesis that the Spearman correlation at the population level is zero against the alternative hypothesis that the Spearman correlation at the population level is non-zero. And you can see in this case that the p-value is 0.0251. And so if we were performing this test at the 0.05 level of significance, we would conclude that at the population level, the variables are related based on, or at least in relation to, this Spearman type of correlation. So we've seen how to do the analysis by hand using a spreadsheet. I say by hand in air quotes here because we are doing it in the context of a spreadsheet, but it does take a little bit of handwork in terms of doing the sorting and entering the ranks and so forth. You could certainly take that algorithm now that you've seen visually how to do it, and you could maybe write your own code to do that if you wanted to, your language of choice. But given that we have this available in SAS, it's also going to be available in SPSS, Minitab, R, and so forth. It's really not necessary to roll your own, so to speak. All right, so that's the end of example 5.1. Let's move on to example 5.2. And in this example, we're going to look at Spearman's rank correlation coefficient in assessing the relationship between lab ranks and lecture ranks. And so the table below contains the ranks of 10 students in the lab and lecture portions of a chemistry course. And so what we have here, the professor had 10 students. In this course, each student is, they're part of the lab, and they also do things in lecture, take exams and assignments and things like that. And so based on their performance, based on some set of metrics that the professor utilizes, he was able to rank the 10 students with respect to their lab work, and also rank those 10 students with respect to their work in lecture. And so we have these two sets of measurements for each student. So again, the columns correspond to the 10 students, and the rows correspond to the different assessments, in this case, for the lab and the lecture components. And so we could consider the lab measurement to be X and the lecture to be Y, or vice versa. It really doesn't matter when we're talking about correlation, because when we talk about correlation, we're really not thinking about trying to predict one from another. What we're doing is we've got two response variables. Instead of having a response and an explanatory variable, we have two response variables, and we're thinking about the relationship between those two variables. And so what we want to do in this example is to calculate Spearman's rank correlation to assess the relationship between the student ranks in lab and lecture. And by the way, because we don't have the underlying data, the underlying metrics that the professor used or may have used to evaluate these students in lab and in lecture, for example, there might be test scores, assignment scores, scores on labs and so forth that the professor used to come up with these ranks. On the other hand, maybe it was more qualitative. Maybe the professor just came up with these rankings based on notes that he took on the students' work in the lab and also their interaction in class. Maybe that kind of information was used to come up with the ranks. We don't know how these ranks were obtained. It could have been from quantitative data, or it could have been qualitative type of assessments. But somehow the professor came up with these rankings. And so in this situation, the point I'm trying to make here is that we would not be able to use what we would call Pearson's correlation coefficient because we don't have data at the interval or ratio level to use to calculate it. So the only kind of correlation that we could use would be this Spearman's rank correlation. Okay, so let's do the spreadsheet calculation, and even though these are already ranks, I'm going to use the same format, the same structure of the spreadsheet, just so that we get used to seeing that kind of structure. Now I'm labeling the lab ranking as X, the lecture ranking as Y, and notice that what we're calling here, the Pearson correlation between X and Y, is 0.85455. Now, we know right from the start that if we calculate the Pearson correlation on ranks, that's already the Spearman correlation. But let's just make sure that that's what we get once we go through this process. So let me go ahead and rank the observations, rank these first 3 columns based on the X value, right? So I get these ranks in ascending order. And then, again, this is really unnecessary, but I'm using the same structure. So, I'll go ahead and do this. But then I have the ranks of my ranks, so 1 through 10. Then we sort the first 4 columns with respect to the Y column. And so we get those in increasing order. And so then we have those ranks here. And now that that's all populated, everything that is necessary for the calculation is done, I will do again one more sort, just so I can get these in observation order. But again, that's unnecessary. Once we have both of these columns of ranks inputted, then we have everything we need. Okay, so we notice here that the Spearman correlation between X and Y, 0.85455, is the same in this case as the Pearson correlation. And that's again because the data that we're applying the Pearson correlation to, or calculating the Pearson correlation from, those are the ranks to begin with. And so we should get the same value. And so that's good quality control check on this spreadsheet and how it's been constructed. Again, because there are no ties in the ranks, the shortcut formula gives us the same value as the definition formula for the Spearman correlation. Now, let's see how to do this in SAS. So, again, I have a data step where I create a temporary SAS data set called set1 containing the ranks that the professor came up with. And then once I have that data set, I'm going to use that. I'm going to feed that into ProcCore. And again, I'm requesting the Spearman correlation analysis here specifically. All right, and you can see here that the Spearman correlation is 0.85455, which is exactly what we got in the spreadsheet. And again, notice that that's the same in this case as the Pearson correlation, because again, the data that we're applying the Pearson correlation formula to are the ranks themselves. Okay, then notice that the hypothesis tests here each of these gives us a p-value of 0.0016. And so that's highly significant. We can see here that there's strong evidence of a relationship between a student's lab ranking and a student's lecture ranking. Now, let me just point out that even though this is labeled a Pearson correlation, we understand that this is actually a Spearman correlation because the underlying data are the ranks. And so we would not interpret this value as the strength of some kind of a linear relationship between lab rank and lecture rank, because when we're talking about ordinal level data, and this rank information is ordinal level, it really is meaningless to talk about a linear relationship. In spite of that, it does make sense to talk about how strongly related the ranks are. This is a strong Spearman correlation, 0.85455, and it's highly significant, the p-value being 0.0016. And so what this is telling us is that those who tend to do well in lab also tend to do well in lecture. Those who rank highly in the lecture part of the course also tend to rank highly in the lab part of the course. And so we really don't need, in this situation, to think of it in terms of a linear relationship, because again, that really doesn't matter, but it is meaningful, it does make sense, and it is helpful to understand that the better one does in the lecture portion, the better they will tend to do in the lab portion of the course, and vice versa. So that's very useful information. So that is the end of example 5.2. That's a realistic kind of example, I think, and I think it's very illustrative in showing how a Spearman correlation is very meaningful. All right, the last example we'll look at in this video, example 5.3, we're going to be using Spearman's rank correlation to assess the relationship between the heights of fathers and sons. All right, and so the table below contains the heights in inches of a sample of 12 fathers and their oldest sons. And so we are going to calculate Spearman's rank correlation to assess the relationship between the heights of fathers and sons. Now, this is data that is at the ratio level. Height data, that is ratio level data. That's the highest level of data. And in this kind of a situation, a linear relationship between two variables does make sense, it's meaningful, and we could use the Pearson correlation to evaluate the relationship, to assess the relationship between the heights in inches of fathers and their oldest sons, and to think of that in terms of a linear relationship. But again, there may be situations with this kind of data where the Pearson correlation coefficient would be perhaps less desirable or problematic if we had a data set where we had a few very tall people or a few very short people. Then that could really impact the value of the Pearson correlation. And so in a situation like that, we could turn to the Spearman rank correlation because, again, the Spearman rank correlation is not going to be focusing. It doesn't take into account the magnitude, in this case of the heights, but it looks at only their relative sizes. It looks at their ranks. And so let's do the spreadsheet calculation again. So I've got the height data for fathers and their oldest sons entered into the first two columns here. And here we've got a sample size of 12, a little bit different sample size. It's still small enough that we can include it on the spreadsheet and show it here. So the first thing we're going to do is we're going to sort the first three columns with respect to the second column, column B, the height of the father, to get those in ascending order. And so we've done that. And then the next step is to compute the ranks. Now, what we need to do is we need to look and see, are there any ties in these values? Well, there are. We can see here that we've got 67 showing up a couple of times. We've got 68 showing up a couple of times. And so because of that, when we assign the ranks, we need to assign the average ranks for those observations that have the same value. So that's what that looks like in this column here. Then we sort the first four columns based on the values in column C, the height of the oldest son. And so doing that, all right, now we see that we have these in ascending order. And again, we have to look and see, do we have any ties? Well, yeah, we do. We see that 65 shows up twice, then 66 twice. We have 68 showing up 1, 2, 3, 4 times. And then those are the only values that are repeated. And so we need to be careful to calculate the correct ranks for the y variable. And so that's what that would look like. And then once we have the rank values in here, we have everything we need. But again, I'm going to sort the first 1, 2, 3, 4, 5 columns just to get them back into the original order of the observations. But again, that's not necessary for the calculation. Okay, so once we do that, we see that the Spearman correlation between the height of the father and the height of their oldest son is 0.74026. Now we can compare that to the Pearson correlation, 0.70265. There is a difference here, but they both indicate a strong, fairly strong relationship between the height of the father and the height of his oldest son. Let me also point out that because there are ties, notice now that the shortcut formula gives us a value that is different than the definition formula for Spearman's correlation. Using the shortcut formula, we get 0.74650. Using the definition formula, the correct formula, we get 0.74026. And so this is a bit off, and it's off because we've got ties. And so in this situation, we can see here that using the shortcut formula would not be advisable, okay, because it's going to give us something different than the correct value for the Spearman correlation. And if we're going to use software anyway, then there would really be no purpose in using that shortcut formula. All right, let's look and see how we do this in SAS. And so again, we have a data step to create a SAS data set containing these heights. And then we just invoke proccore using, this is the same code. We haven't, because I'm keeping the variable names the same, this is the same code that I've used in the other two examples. And so you can see here that it's very easy in SAS to get this nonparametric correlation analysis using Spearman's correlation coefficient. All right, all of that knowledge, all of that capability, all of those formulas are all included in, they're all encapsulated in this particular procedure. And SAS proccore has lots and lots of options, lots and lots of capabilities. We're barely scratching the surface in what proccore can do. All right, we're focusing specifically on performing Spearman's rank correlation, calculating the correlation and performing the hypothesis test to determine whether at the population level the Spearman correlation is different from zero. But there are many things that you can do using proccore, and I would really suggest that you take a look at that documentation to see all it can do. So let's look at the results. And it's always good to check the simple statistics. Yes, it used all 12 observations, so that's good. There were no missing values or anything, and we know that because we saw the data step. But if you're reading data in from a spreadsheet or some other source, you always want to see how many observations are used in the analysis. As I've said before, when you're using SAS, if any of your variables that are used in an analysis have missing data, then by default SAS is going to kick that observation out. All right, and so you need to check to see how many observations have been used in an analysis. But in this case, all 12 observations were used. And we can see here that the Spearman correlation is 0.74026, which is exactly what we got. 74026 right there. That's exactly what we got. And we can see here that the p-value is quite small, 0.0059. And so, for example, if we were testing the null hypothesis that the Spearman correlation at the population level is 0 against the alternative that it's non-zero, and if we were performing that test to, say, the 0.01 level, then we would reject that null hypothesis and conclude that the heights of fathers and the heights of their oldest sons are indeed related at the population level. In fact, there's fairly strong evidence for that relationship. And so that's very useful. And we could draw that conclusion even if the population of heights was not symmetric, if it was skewed. If we had a sample from a population that was somewhat skewed, we could still use Spearman's correlation and have confidence in those results. If we did have a highly skewed distribution, or if we had a data set with some extreme observations, then we may be somewhat hesitant to use the results based on the Pearson correlation coefficient, but you can see that we get a fairly similar result. Both of these correlations would be considered to be fairly strong correlations, and both are significant. You can actually see that the Spearman correlation here is a bit more significant than the Pearson in this case. But the bottom line is that we could draw a conclusion about the relationship between the height of a father, the height of his oldest son, based on Spearman's correlation coefficient, even in the presence of perhaps a skewed distribution. So that's the end of this example. It's the end of what we're going to talk about regarding the Spearman rank correlation. Again, the Spearman rank correlation is a non-parametric type of correlation, and it helps us to evaluate the nature of the relationship between two variables and to test hypotheses about that relationship and to quantify the strength of the relationship, and to do so in a non-parametric way, to do so in a way that really does not depend on normality, bivariate normality, as does the Pearson correlation.